Most applied machine learning workflows begin with a label. Predict churn. Classify fraud. Detect spam. The target is defined before the analysis starts. Supervised learning is powerful, but it depends on someone deciding in advance what matters. There is another class of problem where that assumption breaks down. The data arrives with no labels, no target, no predefined outcome. The question is not what to predict, it is what structure exists and whether that structure is real. That is unsupervised learning. And on structured tabular data, it is one of the most powerful and most misused tools in applied machine learning. A team runs a clustering analysis on customer transactions and produces clean, well-separated segments. The output looks structured. The groups are easy to describe. Decisions start forming around them. Then the critical question appears. Are these segments real, or are they artifacts of the algorithm, the pre-processing choices, and the number of clusters selected at the start? Clustering does not discover truth. It imposes structure based on assumptions. Change the scaling and distances change. Change the algorithm and the definition of a cluster changes. Change the number of clusters and the structure changes. The result is not a fact. It is a hypothesis. That is the context for everything that follows. Build rigorously. Evaluate quantitatively. Interpret cautiously. Clustering is not one method. It is a set of methods, each defining structure in a different way. KMeans partitions data into K groups by minimizing distance to a central point. It assumes clusters are compact, spherical, and similar in size. Hierarchical clustering builds structure step by step. It merges observations based on similarity, forming a dendrogram that preserves how clusters are created. It allows for uneven sizes and more irregular shapes, but still depends on distance as the organizing principle. DBSCAN takes a different view entirely. It defines clusters as regions of high density. Points that do not belong to any dense region are labeled as noise instead of being forced into a group. These are not interchangeable tools. They are different assumptions about what structure looks like. Apply all three to the same data, and each will produce a different answer. The question is not which one is correct. The question is which assumption matches the reality of the data. A clustering analysis on the OpenML Spotify all-time top 2000s dataset uses track-level audio features, danceability, energy, valence, and tempo. The features are standardized, so distance reflects relative differences rather than scale. With 4 clusters, KMeans and hierarchical clustering recover similar structure in the data. One group concentrates at high energy and high danceability, up-tempo, dance-oriented tracks. Another sits at low energy and low danceability. The remaining clusters capture intermediate profiles. The overall pattern is consistent across both methods. The boundaries are not. Cluster shapes differ. Sizes differ. Assignments at the edges shift. That is exactly what should happen. When different algorithms agree on the broad structure, there is signal in the data. Where they disagree, the structure is uncertain, and modeling choices are driving the result. Analysis of the OpenML wine quality dataset introduces DBSCAN on physicochemical features, alcohol content, acidity, residual sugar, chlorides. Instead of forcing every observation into a cluster, DBSCAN identifies dense regions and labels low-density points as noise. That behavior becomes critical in an OpenML customer segmentation comparison using recency, frequency, and monetary features. All 3 clustering families are applied to the same data. DBSCAN returns a silhouette score of 0.84. KMeans and hierarchical clustering fall between 0.55 and 0.57. On the metric, DBSCAN is the clear winner. But the structure tells a different story. DBSCAN produces one dominant cluster, a few small satellite groups, and excludes a large number of points as noise. Those excluded points do not factor into the score, inflating the result. What it finds is a dense core, not a usable segmentation. KMeans and hierarchical clustering produce 4 distinct groups with clear behavioral profiles. Lower score, better structure, more actionable result. A higher metric did not produce a better model. Evaluation does not end with the number. It begins there. Recency, frequency, and monetary value transform raw transaction logs into 3 interpretable dimensions of customer behavior. Applied to the OpenML Online Retail 2 dataset, a real-world e-commerce dataset of UK-based transactions, this transformation produces structure that can be acted on. 4 distinct segments emerge. The largest cluster contains customers with moderate recency, steady purchase frequency, and consistent spending. They account for the majority of total revenue. A smaller segment captures high-value customers, recent, frequent purchasers with strong monetary contribution. This is the most engaged group. Another cluster consists of stale, infrequent, low-spending customers, a segment at risk of disengagement. A fourth, very small group isolates extremely frequent, high-spending customers. Their value per customer is disproportionate. These are structural outliers that require individual attention. This is what clustering is meant to produce. Not just separation, but interpretable behavioral structure grounded in real data. But these segments are not decisions. They are hypotheses. They must be validated against business outcomes before any action is built on top of them. Structured data at scale introduces a different problem. Too many features, too much redundancy, too much noise for a model to extract signal cleanly. Principal component analysis, PCA, addresses this by transforming the feature space. PCA does not remove features, it rotates them. The first principal component captures the maximum variance in the data. The second captures the next largest share, constrained to be perpendicular to the first. Each additional component continues this process, producing orthogonal directions that explain variability without duplication. Dimensionality reduction comes from keeping only the leading components, the directions that carry signal, and discarding those that primarily capture noise. The result is a compressed representation of the data. Less dimensionality, less redundancy, preserved structure. A student performance analysis makes PCA interpretable in practice. Using the UCI student performance dataset from OpenML, which includes behavioral and contextual variables, study time, failures, absences, alcohol use, family support, parental education, and grades, PCA is applied to the numeric features to determine whether they compress into a smaller set of meaningful dimensions. 3 principal components emerge with clear structure. The first is dominated by prior grades, class failures, and parental education, an academic achievement axis. The second is driven by alcohol consumption, social activity, free time, and study time, a lifestyle axis, often inversely related to academic effort. The third combines parental education with grades, a family background and performance axis that partially overlaps the first. This is how PCA becomes interpretable. Each component is a theme built from the original features. Large loadings define what that theme represents. But interpretation introduces risk. Parental education can act as a proxy for socio-economic status. If components like this feed downstream models, they must be documented, tested for disparate impact, and, if necessary, constrained. Dimensionality reduction simplifies the data. It does not remove responsibility. When linear structure is not enough, when the data lies on a curved, non-linear manifold, 2 methods are commonly used for visualization. tSNE and UMAP project high-dimensional data into 2 dimensions by preserving local neighborhoods. Points that are close in the original space tend to remain close in the embedding. tSNE often produces sharper visual separation, but is slower and highly sensitive to parameter choices. UMAP scales more efficiently and tends to preserve more of the broader structure. In practice, both are typically applied after reducing dimensionality with PCA. This limits noise and makes the embedding computationally feasible. But these methods are easy to misuse. The axes in a tSNE or UMAP plot have no meaning. Distances between clusters are not reliable. Different random seeds can produce different structures. And coloring points by known labels can create a convincing illusion that the method discovered those groups. It did not. These are visualization tools, not validation tools. If a pattern appears, it is a hypothesis. It still needs to be tested. Chapters 6 and 7 of my book, Applied Machine Learning, Concepts, Tools and Case Studies walk through all of this with working code. The Spotify clustering comparison, the wine quality DBSCAN analysis, the full RFM customer segmentation pipeline, the student performance PCA with loading interpretation, truncated singular value decomposition for sparse text, and the tSNE and UMAP case studies with trustworthiness evaluation. If structured data without labels is where your work lives, the link to my book is in the description. With the classical supervised and unsupervised toolkits covered, the series now turns to the models that sit beneath all the attention in modern AI and machine learning, but that some practitioners still fundamentally misunderstand. Video 7 builds deep learning from the ground up, starting with a single perceptron and earning the complexity of a multi-layer network, one layer at a time. Unsupervised methods find structure when you have no labels to guide the search. Use them rigorously, evaluate quantitatively, and treat every cluster, every component, every 2-dimensional embedding as a hypothesis, not a conclusion. See you in the next video.